How's it going, everybody? I'm just going to post a quick video. I had someone ask about a video that's just a refresher or a reminder on these various plots that we look at for our case analyses and model assumptions. So I'm going to be using this the bias data that we've used before. So at this point, I've gone ahead and run up to this point. So all I did was I reverse scored the one concern item that needed to be reverse scored, and I computed the post IAT, and then I subset the data to only the variables that we're interested in, and then just for the sake of simplicity and not dealing with any missing data, I subset that even more by just the number of, or just the participants who had all for these three variables, and then I created this mod IAT, which is the model that we want to look at. So looking at post IAT scores predicted by condition and their baseline IAT scores. And so when we run through these case analyses, the first thing we want to look at is this residuals plot. And so when we look at this, I'll go ahead and click finish up here. Since there's nothing, if there were any that were problematic, you would see that red line cut off here. So what this is looking at is that if you take all of the residual values, all the errors for this model and how far each of these are from their prediction, if you take all of that and then studentize it, which means that you're basically putting it in a t-distribution so that you can now put a significance value with that. That lets you know if there are any significant outliers as far as the model residuals go. So if that red line happened to be right here between these two values, then that would indicate that these two over here are significant outliers as far as their residuals go. In this case, we're all good. We don't have any residual outliers. Now I'm going to run this dev off right here just so that I close out this, and instead of each time I run this when it pops up in that secondary window, which kind of frustrates me, instead I'm just going to run dev off, close that out, and now we'll check our univariate distributions. And so when we look at this one for our post IAT scores, remember that the dotted lines are the median or the mean, and you'll see solid red or solid green lines for the cutoff for plus or minus 3 standard deviations of the mean, or 2.2 times the interquartile range for the median. So again, in this case, we can see that there's no values for post IAT that are beyond these cutoffs, and so we don't have any post IAT outliers. If that line was right here and we wanted to see what this value is, we can click on it, and then when we click finish, we can see that that would be participant number 5. But again, that's just demonstrating that's not actually an outlier. So we hit enter to see our next plot, and finish that one, and then enter to see our third plot. Now in this case, we do have a couple of outliers up here. And so if we click on those, and this is for the baseline IAT, if they're at least outliers based on this median value. Now, because I'm not running it in quartz, but instead running it through here, and I use this dev off, whenever I click finish, it's, well, I take that back. I was going to say it should crash, and sometimes it will, and it won't behave, but in this case it told me that's, number 13 and number 19 are both outliers based on the median plus or minus 2.2 times the interquartile range of baseline IAT. So we have 13 and 19. And so run dev off again, and now we'll look at our hat values. And when we look at these, again, we have this cutoff here, and let's check out what these 3 values, or 4 values, there's a 4th one here. Click finish, and we see that that's 2, 13, 19, and 53. 2, 13, 19, 53. And so what this is looking at is, just as a reminder, the hat values, that's your leverage. And so that's looking for unusual combinations of predictors. If you recall, when we were looking at the prestige data set, the sewing machine operators was one that had a really high hat value. And that was because it was just a weird combination that sewing machine operators had very, very, very little education. But compared to other jobs that had such little education, like babysitters, sewing machine operators made a lot more money. So they had very, very low education, very, very, very high percentage of women, but also the amount of income that they had for that combination of low education and high percentage of women was unusual. But if you recall, in that particular model, even though it was an unusual combination, so it had a high leverage value, it didn't have it fit the model pretty well. Its prediction wasn't terribly off from its actual value. So in this case, that's what we're looking at here. We're looking at unusual combinations of predictors, and so we have 2, 13, 19, and 53. Run dev off. And now let's check out Cook's D, which again, Cook's D is overall influence on the model. So it's kind of taking everything into account and seeing overall how much do these individual cases influence the model. And when we check that, we have 57, 5, 9, and 19. And if we take all of these together in the influence plot, this is kind of messy and kind of hard to tell what's what. But the important things, this one over here has a pretty ginormous Cook's D. So just as a reminder, we have our hat values. Our leverage is here on the x-axis. Our studentized residuals is here on the y-axis. And then the size of the circle is it's scaled by their Cook's D value. So like I said, this one's kind of messy and kind of hard to see, but if we just kind of go around and click on some of these that seem a little bigger or whatever, just taking a look, obviously 19 over here is a huge concern. It has a substantial Cook's distance. Its residuals aren't the best. Plus it has this really high leverage value. Up here, this number 9 has a pretty sizable Cook's D as well. These down here, like they're pretty big as far as Cook's D, but really it comes down to anyone might have different interpretations of these graphs, and it just kind of comes down to your judgment and taking all of these into consideration together. So what I'm going to do before we start talking about what does all this mean, you have to take all of them into consideration together. And so let's do this last little bit of running our DF betas, and what this does is it looks at the influence on the specific parameters. So when we run this first plot, we're looking at the individual data points, and let's just say, I'm not saying that these 3 points are outliers, but let's see what they are. So number 66, 53, and 57 all have the most influence on the intercept, and you could maybe you want to make the argument that those 3 are further out than all the rest of these, or maybe even this one over here seems unusual, pushing it in this other direction. but we'll say 66, 53, and 57. And so check our next one, condition. You know, well, maybe we just say just that one is substantially out from the rest. So again, what you're looking at here is this is all of these different cases and how much influence do they have on the slope of or on the estimate of the condition here. So in this case, let's just say just that one, and it's 57. And then if we run it again, now we have our base IAT, and clearly we have one over here that's problematic. These, you know, maybe it just kind of depends. You know, again, a lot of it comes down to kind of judgment and justifying your choices for who you're going to remove or not. Now this time around, when I click finish, it is going to crash. So let me try to run that again, and if I run this one in quartz, then it should now open up in quartz. And so now when we click on it, it'll work like it should. And we can also, while we're at it, we'll check that. So that was number 19 that you might say is high on that end. And so if you're on this external window, at least on Mac for quartz, escape is comparable to hitting the finish button. And so then we'll run the next plot and check those out. And again, like 57 and 9's pretty high, but you know, whatever. So I'm going to hit escape here and then come back, hit enter, go back to my plot, and now we can see number 19 is that one that's exceptionally high. So this is saying that 19 has, you know, outlying influence on the estimate for baseline IAT's effect. And when I say outlying here, I'm not talking about some statistical cutoff or saying that it's significantly outlying. At this point, you're just kind of visually, you're eyeballing this and seeing like, oh, well, like this one seems to kind of stand out from the rest. Like the rest of these are you know, more or less distributed evenly. I mean, obviously there's a lot more here, but even these, they're not substantially out to the side. But that one kind of stands out on its own, and so that's really what we're looking for there. So we'll add number 19 there. Run dev off. So again, this time I'm doing the added variable plots, and this par mf row 3.1 is just telling R that I want 3 plots, 3 rows, 1 column of plots, and it'll be the next 3 plots that I put in. It would help if I have my libraries loaded. And so what we're looking at here is the basically controlling for all the other variables besides the one noted. So for the intercept, controlling for all the other variables, and for the condition, controlling for all the other variables, and for baseline IAT, controlling for all the variables. What are the predicted residuals for all these things? And so in this plot, you're just looking for anything that kind of stands out. Most of your focus should be on your focal parameter. So in this case, our focal parameter is really the condition, and so this is the main plot that we want to focus on and scrutinize. And it doesn't really look like there's anything terribly outlying here. You know, this one up here is pretty high, but it's not like this is the only point up here. I mean, there are others that are just under that. It's not like the others all stop here and then you have this one that shoots way up. Same thing over here, that, you know, 57 is pretty low, but you know, you have a few low points, so it doesn't seem like that one particular case is too terribly concerning. And so what you have to do is now kind of look at all of these holistically, and I'm going to go back and check out this influence plot again. And so when we're looking across this and we start trying to figure out what is it that we are, who are we wanting to exclude from this analysis? Certainly this one that's just, it has a substantial amount of influence in it, as evidenced by this pretty gargantuan, noticeably huge Cook's D. And then maybe this one up here, we think that that one's a little bit too big on the Cook's D value. All the rest of these, like their residuals aren't off too bad, their leverages aren't too bad. You might make an argument for say this one, and that it's got a pretty sizable Cook's D. I probably wouldn't, just because its residuals aren't too terrible. It's not quite past the threshold of high leverage. Same thing with these down here. You could make an argument either way for excluding these or leaving them in. So like 5 and 57. Just for now, just for the sake of time, I'm going to go ahead and just say 19 and 9 are the two that I'm going to take out. So I'm going to remove those two IDs and rerun this model. So now we can look at our model assumptions. So the first thing that we're going to look at is the model assumptions normal. And what we're looking at here is our distribution here should more or less fall along this dotted blue line, and in this case that's what we find. So the residuals look rather normally distributed. And as far as this QQ plot, what we're looking for is that our values fall more or less along this straight line, which again, like this one, seems like it's in pretty good shape. A couple of these deviate off that line a little bit, but again, you're never going to have perfect data, even when it comes from a normal distribution. It's not going to be perfect. So there is some wiggle room, but by and large, this looks like it's in pretty good shape. And when we look at our GVLMA output down here, it tells us that like all of our assumptions are acceptable. But let's take a look at what that means as far as the constant variance. When we look at this, this plot right here is arguably more important to focus on than this one. I'll explain why in just a minute. But when you're looking at this plot where it has the fitted values along the x-axis, or which is the predicted values, and then you have the studentized residual. So again, this is like the previous plot where we talked about. That means that we're converting our residuals to a t-distribution, and then we're able to see if they're significant or not. And so what you're looking for in this residuals plot is you want them to be more or less kind of randomly scattered about but flat. You don't want to see kind of a conical shape like this, whereas fitted values, which is your y hat, as y hat increases, if your error increases as well, then your points will be closer here, and as you move down this line, it'll get bigger and bigger and bigger, and that means that you don't have constant variance. At any given point of this x-axis, if you take all of those points and find the average of those points, and then find any other point on this x-axis and look at, say here, and what are the residuals over here. If you have constant variance, it should be nice and even, more or less flat, and that's kind of what we see here. We don't see that conical shape. We don't have something that's the bow tie shape where the predictions are good here in the middle, but like as you move out to this end, they spread out, and as you move out to this end, they spread out, etc. So on this plot over here, the reason that I said that like don't put too much weight into this plot is because you might look at this and be like, oh, that line is terrible. Like, you look how this pink line like deviates from that. But what I want to point out is I want to remind you that this pink line is a lowest line. And what lowest means is it's that localized thing. So in other words, it's looking for, say here to here, and here to here. Instead of having one line that predicts all of it together, it's looking at smaller units. And so this looks like it bends down, but as you can see, it's because there's this one and there's no other points down here. And so this pink line is going to be subject to more pull where there are less data points. We talked about in drill that typically lowest lines are they're best suited for very large amounts of data, because if you only have single points here and there, it's going to be all over the place. So when you look at this line, it looks, just if you just glance at it and say like, oh, that line is terrible, this isn't good, but then once you stop and think about it, you realize like, oh, it's only pulling that pink line down because there's no other points anywhere down here, so it's localized to these points right here. So in other words, yeah, that line doesn't look great, but don't worry about it, because when you look at this plot, you can see that your residuals are how you want them to look. You don't have unconstant variance here. And then the last thing that we look at is the linearity. And here again, like, you're basically, ideally you would want your lowest line to more or less fall on the dotted line, and over here it doesn't, but again, that's just because you have these values over here that are really pulling that lowest line down, and lowest lines are going to be highly inaccurate wherever there's not very many data points. And so these values right here are what's really pulling that down, but that's not to say that this doesn't fit. Besides that, there's one other thing that is also can be helpful, which is that instead of using the model assumptions, which are great in their own right and for their own reasons, but another thing that you can do is just use plot. And if I talked about this in drill today, if you use plot and put in your model, it'll give you 4 diagnostic plots. And so this first one is your residuals chart, same as the left-hand chart of this model assumptions constant, where you have your residuals on the y-axis and your prediction on the x-axis. So again, here you're just looking for constant variance. You're looking for kind of flat along the top and bottom, and more or less scattered evenly, and not having that kind of conical shape where down here that's nice tight predictions, and as you move down, those predictions get worse and worse, or rather more and more error in them. Or if you have the bow tie shape, meaning that in the middle of these predictions it's a pretty accurate prediction, but as you move out towards the ends it becomes less accurate, etc. Hit enter again and you'll get your QQ plots. And again here, like you can see that, like, yeah, it kind of comes up off the line there and kind of down here, but overall, like, it's pretty close. It's in there where we want it to be, so it's not terribly concerning. Like, that looks fine. And then another form of the residuals plot, but this time it has the square root of the absolute value of the standardized residuals plotted against the fitted values. And so again, you're wanting to make sure that there's not systematic changes in the residuals as a function of the fitted values. And then for the one more, there's the residuals versus leverage. So this is kind of similar to the influence plot, in that you have standardized residuals over here on the Y. You have your leverage, which is your hat value, down here on the X. Now you'll see right here where it says Cook's distance and it has dotted red lines. The reason that you're not seeing it on this chart is because none of them, well, they no longer come close to being excessive in that Cook's distance, because we took out the two that were particularly concerning Cook's distances. But basically, if we had problems with Cook's distance, it'll show up in this graph. Typically, it'll start kind of like rounding out the corners, and so you might see a dotted red line that comes up and over like this, and another one that's kind of up over here like this. Depending on the data, it will put the Cook's distance line on there. If you don't see any dotted red lines, then you know that you're good. But if, for instance, that dotted red line came up across this corner and cut across right here, you could say that this, data point number 17, like exceeded that threshold for significant Cook's distance. And so if anything I just talked about in this like plot portion of it, if any of that throws you off, just ignore that altogether and stick with the model assumptions and model case analysis stuff, and don't worry about using plot. Although, like, this is my typical preference for the at least initial diagnostics. The nice thing about the model assumptions is that you are able to like click on the data points to figure out who's who or what's what, things like that. So it does have some nice features, but you can also use this plot here. So that said, if you have any questions, feel free to let me know, or if I need to better explain anything or just re-explain anything, just let me know, and good luck on your exam.